titled it Testing Made Easy on the schedule, but this is actually kind of an amalgamation of two different topics that are moderately related, but we didn't have enough time to fill. Like each one of these topics was separate. The first one is Google Summer of Code. We had 2 students in Linaro this year who did some fantastic work. Gaurav Minocha, who's right here, did some work on self-testing in the kernel on the device tree infrastructure, making those self-tests work on pretty much any platform. And we also had Varad, what was his last name? Gautam. Varad Gautam, who was working on getting UEFI up and running on the BeagleBone, and I think he was quite successful. But unfortunately, he wasn't able to make it here. So rather than making Gara fill a full session, he's going to present on the work that he was able to do with the self-testing for the first half. And then for the second half, we're going to have a boss session to talk about ways that we can make ad hoc testing for kernels, particularly for kernel maintainers, so that we're easily able to test on a lot of different architectures under QEMU, and then easily extend that to boards, solving the problem of things like getting the root file systems and getting case self-test tools that are in the kernel into those tests. So first, I'd like to turn over to Gaurav, and all yours.
Good afternoon, everyone. As Grant mentioned, that I'm going to present my work done at GSOC 2014. GSOC is a program that is done to promote open source development among students, university students. Linaro was my mentoring organization. As you see, Grant was my main mentor, but Linaro is a wonderful organization. They even give a backup mentor if the main mentor is not available. So Rob was my second mentor. I was doing my master's at the University of British Columbia when I registered for this program. Today I graduated and working as a merit software developer. And what did I achieve from this program is definitely a lot of learning in kernel programming. I have my patches in mainline kernel today. Definitely I earned some good stuff excitement, and I'm invited for this Linaro Connect to present my project done. That's a really wonderful opportunity for me, and I really want to say thanks to Grant. Steve is sitting in front of us. He has managed everything and has been helpful for everything. So let's start with what I've done. Before starting, I need to give an overview on the Open Firmware Self-Test. So Open Firmware Self-Test is a set of unit tests that is written in the self-test.c. So basically, these tests are designed to test the functions provided in the OF interface, that is the OF.h. And the functions in this interface are used by driver developers to fetch the information from the unflattened device tree data structure. Like, if I have to take an example, I would take the OF find node by name that most of you would have used it in your driver while probing. So this is referenced in around 88 files. So this just shows the criticality of these functions being used in the kernel. On top of it, these functions are continually improved and optimized with time. So it's very important to maintain this self-test and regularly test them. I'm sorry. One thing. Oh, sorry. There is some problems. Okay, so there was some switching in the slide. So steps to execute the OF self-test. Step 1. What we do is, these are the traditional steps that used to happen. So you manually find the device driver file, the device tree that you will be booting the kernel with, and you're going to be editing that file, and you will add your test data that you need to that is required by the self-test. You'll add it into the this device tree, and then you're going to be compiling that device tree source file into the DDB, and finally you will boot the kernel with that DDB. So, and definitely you need to enable the kernel simple OF self-test so that you compile the unit test that will be using the test data. So the problem here is the manual process that is involved in finding the file of a particular DBS that you want to boot the kernel with, and then you have to edit in. On top of it, even after your tests are done, the test data remains into the tree. So it's sitting in the tree until and unless you reboot the kernel with the fresh DTB that has no test data in it. So the solution is to remove the manual process. So for this is a summary of the steps that will be discussed in detail ahead. Step 1 is to compile what we will do is we'll compile the DT source file, that is the test data file, separately into a flattened binary blob. And then we'll link the binary blob to the kernel image. Once we have this in our kernel image, when we are booting the kernel, we will read this blob into a local, we'll copy this blob into a local in the memory, and then we'll unflatten it. After unflattening the device tree, we will pick each node from that tree and we'll attach it into the live tree. So this is handling, everything is being here done dynamically. Prior to this, it was done statically. We added the file into the device tree source file itself. So now there can be two cases. Either the library is present or either the library is not present. Maybe the system is not booted with the device tree. In that case, the test tree will become the library. And if it is present, as I mentioned, it will be attached to the tree. And in the end, once we are done with the test, we'll remove the test data. So we will clean the system dynamically itself. So the test data doesn't remain in the system. So, okay, before moving ahead, I'll just remind you about the device tree source file. It is arranged in form of nodes, and the root node, as you see in the blue, contains the test data. And test data further contains other nodes that will be required in testing. So it's arranged in that form only. This file is compiled to a DTB, that's the flattened device tree block. So coming back to our step 1, compiling the DT source file. So build this file, you need to mention your make file. Prior to, traditionally only selftest.o was part of the selftest objects. But today we also have to let it know that you have to compile the test data along with it. So here, as you see, the test case is .dtb.o. That's not DTB. It's just DTB.o because it has to be linked to the built-in when the kernel is being built. So all the rules are called in chain, but this rule is the last rule that is used to convert the DTS to the DTB. So now we have the DTB from the DTS, but that's not sufficient for the kernel. We have to we have to link it into the kernel. So for that, we convert the DTB into DTB.s. Now this .s file is used by the sampler to convert it into .o, and finally it is linked by the linker into the kernel image. But apart from this, if you see this make rule, you will find two global symbols. That is the DTB. In this make rule, I've just tried to show the global symbols because these global symbols mark the beginning and the end of the device tree block. So in the kernel symbol table, you will find these symbols mentioned, just defined, telling you that this is the point where my device tree blob is starting, and this is the point where it is ending. So I will explain it to you what's the importance of it. And that's going to be like DTB, the file name begin, DTB file name end. So to summarize, the .dts file is converted to .dtb, then DTB to .dtb.s, then DTB.o, then finally linked to the kernel. Okay, so now coming to step 3, where now you have booted the kernel. Now it's time to read the flattened device tree block that was linked into the kernel image. So as you see that we are using the external keyword and getting the DTB test cases _ begin. So this is the same symbol that was used in the makefile to mark the beginning and the end. And these two symbols are used further to get the data, the blob at the runtime. So you get the size, or how much the size is, and create a copy of it and store it so that it can be converted further into an unflattened tree. So now the step, as I mentioned, it comes from, now we have to convert the flattened device tree to an unflattened device tree. So for that we have OF flattened FDT unflattened device tree function already available that will convert your flattened device tree block to the unflattened tree. Unflattened tree, I will show you in the next slide what it looks like. And then, as I mentioned earlier, if the library is present, it will attach it to the library, the nodes to the library. Else, it's gonna attach the test data as the library. So now we are done with this flow, and we have the unflattened FDT in the system memory. So this slide is just to mention that, as you know, this device node structure has many members, but the main thing that you have to see is that, like the name suggests, the parent, child, and sibling. As the name suggests, you know that every node in this tree may have these pointers, so to construct the tree structure. But there is another node, there is another pointer that says all next. So basically, there are two structures, two data structures. One is a tree data structure, and you see, and there is one other linked list data structure. So all next is used as a linked list. Basically, it's a list of all the device nodes in an order that I will show you later. It's an easier way to traverse the tree if you are. I will show you in the next slides. So coming to the unflattened device tree, I've used the colors here to show the branches. So if you see, the blue branch is one branch, blue, and the red, the green, and pink, that is the root node. So basically, if you see here, major role is of the child and the sibling pointer. So every node has one child pointer, and every node has a sibling pointer. So if a parent is this, it is pointing to a node. It has only one child, right? But it has many children. It has children. But all the children are linked in a form of list using the sibling pointer. And so basically, the all next pointer. So basically, the child, sibling 2, sibling 3, sibling 4 all have a parent pointer pointing to the root node, and the all next pointer is like the list that are shown here: the root, child 1, child 11. So first, the path of following the linked list is like first go to the child, then go to the sibling. So if you follow that, you're gonna see that it's going first to the blue part, and in between there is in blue sibling 1, 3 that has a child. So first it goes to that child, and then comes back to sibling 1, 4. That's how the whole list is generated. Okay, so now it's time to attach the device nodes. That's the main thing. So to explain this, to explain how to attach the test data to a tree, we will take the sample tree that's shown here. This is the tree we obtained after unflattening the flattened device tree block that was in the kernel image. So this is the sample tree we have taken, and we will be attaching it to this tree. That was we are assuming this is the library of the system. Okay. So when the test data is attached to the library, now this is the final structure. Though I have collapsed because the slides have no space, I will show in the next slide the exact full structure. The test data tree fits into that quarter and shifting the actual child of the root node to the right. Okay, so what happens is basically whenever there is a node sent to attach to the tree, what it does is it sees if there's a child, it's gonna be the node makes itself the child. Whenever you send node, first you give a parent. You have to give a parent to that node. Basically, the parent pointer cannot be null, because if it is null, it doesn't know where to attach, right? So I'm not considering the case of a root node if you have to attach a root node. So once you attach, you send with the parent. So if the parent already has a child, so it's gonna what it's gonna do is that node will take make that child its sibling and make itself as a child. So that's why you see that the child has been shifted and it made itself as a child of the root node. So when we send the test data, we have to make sure that test data's parent is pointing to the root node of the library. This we have to set it before. Yeah, that's what I said in the mention. The test data has a root node set to its parent. I hope I'm not missing any point here. So that's the expanded view of the test data. Basically, the test data that has been added, and I've collapsed the other part of the tree so that it's more visible now. So you see that test data and the test sibling 2, 1, test 0, and all have been adjusted into the tree. The thing you have to note here is that test child 0 node becomes the last sibling compared to the earlier structure. In the test tree that was supposed to be attached, the test child 0 was the child of test data. Now it has been shifted to the corner. Because when it was being attached, so when you are attaching, so you keep adding a node, and that, as I told you, when you add a node, it tries to make itself a child and shifts the other node as a sibling. That doesn't make a big difference because they are all the children of the same, but it's a structure that has been designed like this.
There's no ordering built into the structure, but this is a side effect of the open-coded list implementation that Devicetree uses. That in the future we want to get rid of entirely and use list head so that we can then move and use RCU and some of those things. But anyway, keep going.
Okay. Yeah. So this is one thing that should be noted here. And one more thing: if you're trying to attach something node in the system, and you find another similar same name node in this library already, so you cannot do that. Basically, when I say same name, it's like the same path. It's like not only same name. So exactly same name, same node is present. But you're trying to attach a node with different properties. So what we're gonna do is we're gonna take that node and update the. You won't attach it. You'll take its properties and update it into the properties of that node. So basically, you're not creating a duplicate. You cannot create, first of all, duplicate in the tree. So you're avoiding that case and still managing to update the properties. And yeah, so this was the case when the library is present. If the library isn't present, then you need to, as I mentioned earlier, you need to make the test tree as the library. So in this case, what we do is you don't need to use any more attaching nodes or stuff like that. What happens is our system identifies the trees with the pointer OF all nodes. OF all nodes is the pointer that stores the address of the root node of the tree. So if OF all node is null, that means there is no library present in the system. So to attach the test data tree as a library, what you do is you take the OF all nodes and make the root node of the test data that you skipped earlier when you were attaching to the library. You didn't attach the root node. You attached from the test data, but right now you will take the address of the root node and put it in the OF all nodes. So now OF all nodes becomes your library. That points to your library and it becomes your library. So in both of the cases are handled. If you don't even provide the test data Devicetree to the kernel while booting, still the test cases can be executed. Okay, so whatever I discussed, I'm going to bring you with the code. This is not the complete code, it's just a snippet, just to give an idea. So you see, I'm traversing the all next list. The all next pointer is used for the linked list. So I'm traversing the linked list to attach the nodes. And if there is a node found, duplicate node found, it is being updated. And if there is the duplicate, it's not a duplicate node, then you are calling the OF attach node to attach the node. And you can see in the OF attach node, we ignore the sysfs. I'm ignoring the sysfs specifically in this slide because it's still under discussion. We are working on it. And so you go to the OF attach node. OF attach node, what it does is, if you see the board, the NP sibling, as I told you, NP is the node that is being attached to it, makes its sibling as its parent's child. So the child is shifted as a sibling. And NP's parent's child becomes NP itself. So it makes itself the child. That's what I was explaining in the previous slide. Rest are also important, but not that important, the one that I was. Okay, so now we are done with attaching the nodes to the system. So it's time to clean up, and we are done with the execution of the test. So it's time to clean the, remove the device nodes. So to remove the device nodes, we're going to be calling the self-test data remove, and while removing, it's going to be calling the detach node. And detach node is just a recursive, it's a recursive call, recursive function. It goes, it cannot be, nodes cannot be, should not be detached from the top. It's detached from the leaves. So if you see, it digs down in this function. It's calling the child, NP's child, and it's going to go dig down to the child, and then it's going to dig down to the sibling, and then from the last corner, it's going to pick the node, start attaching to in the backward fashion. Yeah, that's all important in this slide. So in the code to see, that was the code for where the detach node and children is called. From here, in the self-test data remove, where a couple of checks are done, because in the beginning, as I mentioned, there was an update. There was a condition in which you check that if there is a node, duplicate node, you update the properties. You have to handle all those cases. So I'm ignoring those cases and just saying that this is called. And finally, the OF detach node also. So now detaching a node. How a detaching would work? Because I told you there are two data structures. One is the tree, and the other is the linked list, right? So linked list detaching a node is simple. Like you take a node out of it, and you attach the two nodes, the previous and the next node, right? And the tree, three things can happen. Either it's on the root, either it's on the it's a child node, or it's a sibling node. So if it's a sibling node, it's again a linked list. So you attach the previous sibling with the next sibling. If it's a child node, you attach the parent, remove the child and make the parent its sibling as its parent's child as its sibling. And if it is a root, then you handle the cases. Basically, you change the root itself. That's what is being done in the remove node, and that's how it's done. As I told you, it digs down and goes to the child and removes the node from the test child 0, 1 and goes back to the test data. And finally, it's removed, and the root is linked back to the child 1. I didn't ask for any questions. I hope there are no questions.
Just ask at the end.
Huh?
You're doing fine. Ask at the end.
Okay. So what's next? It's done everything. This thing is already in mainline now, but as you see, the pattern of adding the child node was reversed from the test data. That doesn't make a big difference, but we can still improve it and make it. When you're attaching a tree, we should make sure that it is attached in the same structure that it was sent. Coming to the second point, right now our whole this self-test is dependent on the OF dynamic flag. It was dependent. Right now I'm working on it, so we have made it independent by using the functions that are required for OF dynamic into the self-test itself, so that it's not completely exposing the functions to the core community, so that because those functions might create problems, as mentioned by Grant. And the next step is we can add more unit tests to the OF self-test, and definitely the unit tests, the OF self-tests are not complete. There's tons of functions in the interface that needs to be done. Right now we have 73 tests if OF dynamic is disabled, and 91 I think if it is enabled, if you are using the dynamic. So there's a lot of functions. Then it is just testing 8-9 functions, because each function has multiple test cases, so it's like it has a lot of scope for the function. And coming to the last one is like refactoring the device tree structure now, as Grant has suggested today. Refactor the device tree structure into migrate into a read copy update that I'm not pretty much aware. And if you want me, do you want me to show the little demo?
If you've got a demo, sure.
I just have my code up there, and I hope I have it. So that's it, but I'm just giving you a demo of what was done.
While he's getting this set up, this was actually an incredibly useful project, because I think I was the only person running the self-tests, because self-tests were only easy to run on the Versatile platform, because I happened to, in the kernel, hard link the self-test code into the Versatile device tree, so it was always there, the device test data. Now basically these test cases run on any platform. We can run them on x86 on ACPI platforms. In fact, I booted one of the ARM ACPI platforms on the model yesterday, and I forgot that I had left the device tree self-tests on. They all passed. No device tree at all, but they all passed. So.
Okay, so this is the this is going to run on the ARM architecture, and it's going to use the versatile machine. And it will be not booting with a DD. There will be no device tree supplied, but this code has been a little step. It is basically what I mentioned, that OF, it's not dependent upon OF dynamic anymore. So OF right now, OF dynamic is disabled, so you're going to see only 73 test cases that's going to be run. So here you're going to see that all the 73 test cases passed, plus because there was no device tree present, as I mentioned you in the beginning, so it should not leave any device tree in the system. So there is no device tree in the POC directory. That's what I'm trying to show. So what was added was removed, and that's it. So DOS should have gone to the sys directory, but it's not there. So going out of there, it's not accepting my command anymore. Okay, so the next would be like to run it with the DD. So now I'm supplying the device tree with the booting. So again the 73 passed because the dynamic is again disabled. If you see, if you so right now you're going to see the device tree is there, and you won't find the test data in it because it has been removed from the system. And you can the case I said, the duplicate node is basically the aliases node, and if you go to the alias,
that's okay. We can.
Okay. So you won't find the alias in the aliases node. And it was tested on x86. I have other systems also on it. So it was tested on x86, PowerPC, and ARM architecture. I think that's all. I mean, and again, I would like to say thanks to our mentors who have guided me and even made it possible to put my code in mainline. That wouldn't have been possible that fast. It was just a 12-week project. That's it. Thank you. Thanks a lot. And if you have any questions, definitely.
Yeah, questions for Gaurav, and then we'll go into another discussion.
Maybe this is a bit of a naive question. What sort of errors does this sort of testing catch?
This is unit testing. This is catching the problems with the core code. And this has been incredibly useful because now as a maintainer, because Gaurav got this work done, I'm able to ask people, okay, you gave me a new API, give me a test case for it.
So basically, as I mentioned in the OF find node by name, the test cases are like without name, with name, wrong name, bad name. So all the small test cases, the unit test is going to cover it. Because tomorrow to change the functions implementation, you don't know if it fails, it's being used by so many drivers. So, For me, it was like protection.
I think John had a question first.
I had a question. Yeah, sorry. I had a question about the unit test output. Is there a specification so that you can say this is the test case and this is the result? Because I see that you list the number of passed and failed test cases, but I'm thinking for something that needs to parse this and extract data out from it, is there a specification that we can rely on so that we know that the output is not going to change over time?
I think there's nothing like that, but again, I've not written the test.
This is grant likely standardized test output.
Okay, all right. So you write the spec then?
I threw that together because I needed some outputs.
Okay.
So I am. This has actually been. This whole exercise has been really useful, and that's one of the things that I want to do more. To start doing more in-kernel unit testing on. And there's other subsystems that are doing unit testing, but to be able to get that output out of the kernel on every single boot, because I think that's a good lead into kind of the next half of this discussion. Is we had a big conversation at Kernel Summit on what are the things that we need to test. There's all these k-self-test binaries in the kernel, which is great if you're running on x86 or if you're running locally because you run them locally. But we can't cross-compile them right now, and we don't have an easy way to get them into a file system. So we had a bunch of conversations about that, and we also had a bunch of conversations of anyone doing testing has to go somewhere. Has to go and set themselves up an environment to test. I mean, one of the things that, one of the big topics that we had at Kernel Summit is, can we have a tool in the kernel that you just go, test all, and boot on QEMU on all these architectures, and then be able to extend that into bring in other platforms.
I guess I would just like to see us have one way of displaying those results, whether that's k-self-test, whether...
I would love suggestions on the best way, on the...
So
yes, I know, you've got an idea.
I don't know, I didn't catch the very first part of what you said, but my suggestion is we should use the test anything protocol. If you look, there's actually a test anything protocol website that has the specification. It's a very, very simple text-only specification. Yeah, okay, our display.
Okay.
Should test anything protocol, yeah. Oh boy, bike shedding already.
Okay, let's hold off on that one for a second. I think John had a question as well, so let's get the questions out for Garo first.
A little tangential to this, but it's related to Device Tree. I was curious, is anyone for future projects thought of doing something like a type checker for Device Tree? I know Brian Sweatland was complaining about it.
And it's stalled. We've got 2 implementations of type checking for Device Tree, which is 2 more than we used to have. But they're both out of Tree on Device Tree compiler. And we don't have anyone, no one's had time. So we need to get an engineer on it.
I started one.
We have 3. 4, okay, we have 4.
So it's not needed.
No, but that is something that's come up. One of the things that we need to be doing with that came up over and over and over again, this Connect, is U-boot is really important. We've got to have some engineering to. There's some new features that we need in U-boot, and there's also just make sure that all the ARM board support is flowing into mainline. But the other big thing on like core architecture is we need some engineers whose full-time job is device tree infrastructure, maintaining those DTS files, getting the type checker into DTC, and making it easier to build these things. Yes. Actually, that's one of the things with Device Tree is we need to get someone working on making sure that the UEFI Device Tree integration is well done. It's not a hard thing to do; it just needs to be done. Any other questions for Garo?
So it runs on QEMU, right? Is there any point running those tests on the real devices? Yeah, but you can't probably do it in an automatic way like it's done now.
Anyone can run these on their real devices by turning on config OF self-test.
It just needs to be built during the build, right?
You just build the kernel with that configuration option and the self-test run. So yes, please run on your hardware.
That's my plan.
I don't know if there's a whole lot of value. I wouldn't ship it on production devices yet. There's a couple of niggly little bugs. One of the things that this doesn't do is it doesn't resolve p-handle references. So you can end up with a short window of time where you have duplicate p-handles in the tree. And that's a bug. It needs to be fixed, but it's self-test code. I was confident merging the code even though I knew that bug was there because it's just self-test code. Don't put it into your production system. But even if you did, the window that bug could be very, very, very small. Any other questions? All right, well, let's talk. How are we doing on time? So we've got about 10 minutes left before lunch. Do we want to talk about the implementation of which way to go with the kernel testing?
Yeah.
Yes. Okay. Okay, so let me talk a little bit more detail about what we talked about at Kernel Summit. The project there was basically 3 conversations that we had in this kernel testing. It was the case self-test, getting that running on cross architecture. There was having an easy tool in the kernel to just boot and test these things. And the third one, which is a much smaller one, is doing more testing like this stuff here, where we've got unit tests in the kernel. And that discussion didn't actually go we didn't go very far. It was brought up, do we have common infrastructure? And I think that the general thought was, this isn't hard stuff. Any common infrastructure would be tiny, but so that would be something that would talk about more if the output formats of unit tests in the kernel. There's all kinds of unit tests in the kernel that we could be doing. What output format would be useful? So, on the other 2, the case self-test binaries. Right now, that's just a matter of programming. That's a matter of someone caring about it and figuring out how to get the makefile scripts to do cross-compile.
Well, don't we automatically inherit cross-compile from the top-level scripts, or is something going on there?
It's just bugging makefiles. It uses the host CC. So
or it just says GCC.
Or it just says GCC.
Oh, so does it actually? It doesn't use like capital CC.
No, some do. Some of them are also called GCC, and some of them
Yeah.
breaks my stuff too.
Oh,
Yeah. So I mean, those tests were just thrown in there of, okay, we've got these tests, let's get it into the kernel tree. Now it needs to be polished up, and someone with some time and understanding of getting across compiling needs to fix the scripts.
well, so one of the questions I had was like I'm pushing this output format, right? So assuming that we get some agreement on output format, who is is that in order to kind of promote that? Is it okay if someone just kind of goes through all the stuff that's in the case self-test directory and starts changing that, or
Yes.
are people going to complain? Who's the owner of the stuff in there? Well,
No.
I checked the maintainers file then.
The owner of it, I can't remember. Her name has flitted out of my head.
Shua,
Yes, she owns it.
So she owns the stuff in that directory?
Yes.
Because I thought she
And
had
she
pulled
wants-
it
she's
from
asking
other
for help.
places, and so there's not like kind of residual maintenance from the person who originally wrote it? Or?
Ignore this people.
Oh, okay.
No.
Well, that's
actually,
my
no,
question.
that's a serious answer.
Do I have to? How much
She owns that
consensus
directory.
do I need to get?
It works for her, but she knows that it's broken.
Okay.
And so she said, she hasn't had time to investigate
So
it.
be aggressive
She's asking
about
for help.
patching stuff.
Absolutely,
Okay.
absolutely.
That's what I wanted to know.
What they should be with help, because I wanted to at my tests, and I was looking at it, and I was like, I don't know what I need to change my formatting to, so
Yeah.
I just
Right.
tried that.
Yeah, I mean, we want to integrate it to be appropriate, so absolutely.
Right. Okay.
And Tim, I think we should, whoever wants to do that too much stuff, we should do it now. Then,
Yeah, I'm-
otherwise, the anti-test stuff, we can do that before we
Right,
start.
right, before you. Well, that's why I wanted to clarify that. I'm happy to go in and spend a couple of weeks going through the existing stuff and.
Yeah. It's just a set up a document of what it
Right.
should look like, so that the new stuff gets added.
Yes, yes.
Don't resist me too hard to say we test anything.
The one item that turned out that looks to be the biggest pain, though, is making it easy to cross-build. Cross-building the kernel is easy. It's the cross-booting the kernel that's really hard. And ARM is easy, x86 is easy, PowerPC is easy, Spark
No, but I
is
still-
easy-ish. But there's a bunch of other architectures
Right.
that. What's that? Both.
Yeah, I'd like to see both, but I think we ought to solve the QEMU problem first.
I agree.
Just do it in a phased
I
thing.
agree.
Because it would be really cool to be able to, from the kernel command line, if you have the tool chains installed, modular
Yep.
that, you just be able to say, run this test on a bunch of architectures, just on my local x86 box.
Yep.
It'd be super, super nice.
So I've got a script right now that I've been fiddling with, and I've been fiddling with PyBoot that Kevin's been working on, and I stole a lot of ideas in a new version that I wrote.
You mentioned TTC in one of your.
There's TTC as well.
So
yeah.
do you have that? Because
I've got
you
you.
asked me for it and I didn't send it.
I've got your latest. I used the intertubes and I found a copy. of
But yeah,
TTC.
there's one up on elinux.org. So it's a little bit old, but it's perfectly functional for.
Yeah. So it's
TTC is
test-
my equivalent of your PyBoot. It's my thing that
Yeah.
abstracts all the differences between
Yeah.
how do you get a kernel on board, how do you boot
Well,
board.
there's kind of an odd combination because there's you need to build the image. We need to build a kernel.
Right.
We need to build a root file system, and then we need to do the boot. And those things, the tools, it's very easy to start kind of merging those things. And I'm trying to come up with a clean architecture. Right now, I've got a nice script that will do the root file system build for BusyBox, and it's in a way that I could pull in the K-self test or pull in perf or pull in other tools. My goal has been the absolute bare minimum. So I don't want to do Yocto, I don't want to do Open Embedded or any of those others
Yeah.
because they solve the problem for big
Okay, so that begs the question: do we actually have to build that, or can we just have some binaries sitting around? I mean, it's like a binary that we could build, and we might not have to touch it for like 3 or 4 years.
Yeah, you see, that's painful.
Well,
That's
I mean,
the
you
thing
should
that
be
I
able to
found.
build what's in the binary. I'm not saying that,
Yeah.
but I'm saying that, if I'm your average kernel tester, do I actually want to have to rebuild BusyBox 7 times to test this on 7 architectures?
BusyBox isn't the problem, though.
You do need to insert kernel modules from that,
Right.
Yeah.
Right. So you need that.
Now, I've got a
Totally.
script to do that.
We should definitely have a baseline process, at least one we know that supports all the stuff.
Right, but
Right. The whatever library you need.
Yes.
that's what I'm concerned about. So it may be it may be a little ambitious to try to solve building the root file system and being able to rebuild the binaries in a tool that lives in the kernel tree. Maybe the first step is just, okay, here's our canned BusyBox binaries. Go get them, and then we will insert the extra files that we need into the root file system. That might be the sane first step, because that gets around the big problem of we don't have a full set of tool chains with an with libc built into them for all the architectures that we can be testing.
Well, the simplest thing I've seen, and it's come up several times on the mailing list, is Aboriginal. And so I spent a couple of weeks looking at that.
Yeah.
You can actually do it, but the root file system you end up with when you're done is not like a full-featured root file system. And I don't know how well it addresses what's needed in K-self-test, but it's very. I mean, it's like really simple to understand. I mean, it's way smaller than. I think it downloads only about 6 packages.
Yeah.
And then, well, there are 2 variants. There's a BusyBox variant and a ToyBox variant.
So, I mean, between that's a total tangent, between BusyBox and Toybox, which is easiest to be working with here? I mean, I've been using BusyBox, should I be looking at?
I don't think
instead?
Toybox is ready yet,
Okay.
personally.
So I use Visual Linux before I have to make it actually work. So see if it works. If it works, it's great. But builders, yeah, go. Builders.
Yeah, Bill, the big problem that I've been having is because I've been trying to do this for the non-easy architecture. I've been trying to do it for Microblaze, or I've been trying to do it for Spark. I've been trying to do it for there's a couple others that we've got QEMU models that'll boot Linux on. And it's once I get off the beaten path that this becomes really hard.
Yeah.
And that's why I want something as simple as possible so that it can also be used as a tool for architecture bring-up.
What happens if you don't have QEMU like HDR32? That's that architecture level.
If we don't have QEMU, we don't have QEMU. It's basically you have to have hardware. I really like the PyBoots, the kind of the general concept of PyBoots. And I'm doing some serious refactoring to make PyBoot actually have an object model of abstracting. Here's the QEMU machines. Here's the machines that are connected to through ConMux. Here's the machines that are connected through. No, I had trouble finding how that worked in there. Well, we should sit down.
4 of the 38 boards are actually QEMU models.
Okay. How are we doing on time?
That build group or that BusyBox doesn't have to run the stuff that's already in KSelf.
Oh, I don't know.
I don't know.
Yeah, I expect it's not.
A lot of the KSelf test stuff is just .c files. So it would be a bigger question of do we have the right libraries in there? If you use just libc, it's easy.
And are they statically
Weak.
So only libc tests, or
Weak.
using anything complicated, pthreads or threads, yes.
Pthreads.
Yeah, there's some pthreads.
So we need the pthreads library.
Yeah, you do need some period. I don't know about like the others, like UCLibc or.
The other least common denominator thing that always comes up is manifest root, MFC root, init manifest. I mean,
Yeah.
Init manifest is clearly the least common denominator, but it also means small.
Yeah.
So I don't know if that got discussed that too. So I like init manifest because it's
Me too.
It's self-contained.
That's kind of how I feel, is that we just get the least common denominator working. We can always grow it out from there. But I would like to be able, I'm tired of dealing with patches and not being able to just say back to the submitter, run this command because I found a bug when I was doing my testing. You fix it, and I don't want to see you again until you fixed it, and here's the tools to show you that it's broken. And I don't have that right now. We're at 1 o'clock, so I don't want to hold everyone up for lunch. But keep talking about this. Thanks, everyone.